first thing I want to look at today is a circle. We're going to label each angle with its degree and with its radian measures on this specific circle here. And remember, we'll start in standard position, which is the positive x-axis. And I'm going to say this is 0 degrees. And then if I were to rotate all the way around the circle, I would end here at 360 degrees. If I were to go halfway around the circle, what's half of 360? 180 degrees. If I were to go a fourth of the way around the circle, like say 360 divided by 4, I'd get 90 degrees. And if I were to go 3/4 around the circle, I'd get 270 degrees. Remember, we always rotate positive x-axis. There's 1/4 to 90, 2/4 to 180, 3/4 to 270, 4/4 to 360. And that's the idea there. Now, if I were to do this in radians, we talked about radians would be 0 and 2 pi. 0 radians is the same as 0 degrees, and 2 pi radians is 1 full rotation. That's the same as 360 degrees. Okay, so that would be the other side of this idea here. Now, if I were to do a half circle, but I was going to do it in radians instead, I would say, what's half of 2 pi? Basically, 1/2 times 2 pi, which would be like 2 pi over 1. So I'd get 2 pi over 2, which simplifies to pi. So that's how I'd come up with a half of the circle in radians. And then I could do 1/4 of the circle as well. 1/4 times 2 pi, which is 2 pi over 4, which is 1/2 pi, or pi over 2. That's what 90 degrees would be in terms of radians. It'd be pi over 2. So the way I like to solve these types of problems is to think about it in fractions. Like, what fraction of the circle am I talking about here? So when I'm talking about 1/4 of the circle, when I talk about 1/4 of the circle, I'm talking about going to pi over 2 radians, or 90 degrees. When I'm talking about half the circle, I'm talking about going to pi radians, or 180 degrees. When I'm talking about 3/4 of the circle, 270 degrees, or I can say 3/4 times 2 pi radians, which is going to be 6 pi over 4, which is 3 pi over 2. So that means 3/4 of the circle is going to be 3/2 pi radians, which makes sense because technically this is 4 pi over 2, right? We do 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. It's just that 2 pi over 2 is simplified to 1 pi, and 4 pi over 2 is simplified to 2 pi, but we're counting by 1/4. 1/2 pi over 2, or 1/2 pi, 2/2 pi, 3/2 pi, 4/2 pi. That's how you'd count by radians. Now we can count these as well. We can divide by even more. Like, other important angles we've talked about is a 45-degree angle is a really important one. That's half of 90. What's half of 1/2 pi? Or what's half of 1/2? If I was thinking about writing this in radians instead. So I'm not worried about the pi too much, but I'm just saying I got to take half of that. Pi over 2 times 1/2, or 1/2 times 1/2, which is pi over 4. That's what 45 degrees would be in terms of radians, is pi over 4. And now, if I did 90 plus 45, I'd get 135 degrees there. So there's a 45 degrees, 90 degrees, 135, 180, add another 45, that gets me to 225 degrees. Add another 45, that gets me to 270. Add another 45, that gets me to 315. Add another 45, that gets me full circle 360. Now, if I were going with radians, excuse me, this is technically 1/4 pi. That's 1 dividing the whole circle by 8. But that might be hard to think about when we keep going up. But what we can do is we can count from here. This is 1/4 pi. This is technically 2/4 pi, simplified to 1/2. That makes this 3/4 pi. I'm just counting by 1/4 all the way around the circle for every 45 degrees. But I'm going to do it by radians. 1/4, 2/4, 3/4. 4/4 pi is the same as 180. 5/4 pi is 225. 6/4 pi is the same as 3 pi over 2. 7/4 pi is 315 degrees. And 8/4 pi is the same as 2 pi. So we're just counting by fourths all the way around. And that's how we want to think about radians. Think about them as fractions. Don't worry about the pi. Just think about it as like, hey, that's 1/4 times pi. That's 1/2 times pi. That's the way I'd look at it personally. Just think about it as fractions when we're counting our way around the circle. Other important angles to deal with are 30 degrees and 60 degrees. We talked about 30, 60, 90 triangles in Mod 5. We talked about 45, 45, 90 triangles in Mod 5. So if I were to count by 30s, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330. That takes care of my 30s and my 60s. Now, if I were thinking about the pi here, the radian measures, and I want to say 180 degrees is 1 pi. What's 60 degrees going to be then? How much of 180 is 60? That should be 1/3. So that's like 1/3 times pi, or 1/3 pi, pi over 3. And if I were to count by 60s around the circle, I'd be counting by 1/3 the whole time, because I'm going to have 1 pi over 3, 120 would be 2 pi over 3, 180 would be 3 pi over 3, which is the same as pi. That's perfect. 240 would be 4 pi over 3, 300 would be 5 pi over 3, and 360 would be 6 pi over 3, which is the same as 2 pi. So I'm seeing that same thing where some of them simplify, but I could count by 60 degrees or pi over 3 radians all the way around. 1/3. 1/3, 2/3, 3/3, 4/3, 5/3, 6/3 is the same as 2. So that's how I'd get the full circle. And then the last one, I would need to count by 30s. And to count by 30s, I have to think about, it's got to be half of pi over 3. So pi over 3 times 1/2, that's going to be pi over 6. That's what counting by 30s would look like. I'm counting by 1/6 the whole way around the circle. And that would make sense too, because 30 degrees is 1/6, 60 degrees is 2/6, or 2 pi over 6, which simplifies to 1/3. 90 degrees is 3 pi over 6, 3/6, and that simplifies to pi over 2. 120 degrees is 4/6. 150 degrees is 5/6. 180 is 6/6. 210 is 7/6. 240 is 8/6. 270 is 9/6. 300 is 10/6. 330 is 11/6, or 11 pi over 6. And then 360 is 12 pi over 6, which, again, a lot of them are simplified, but some of them aren't. So that's how we'd come up with all of our radian measures for this entire circle. And this is going to be useful for us because these measures account for the entire this entire circle. These are what the corresponding radian measures are for each degree measure. So it gives you some easy ones. If I ever give you a 30, a 45, or a 90, any multiples of those, you should be able to use this circle and say, oh, that's a radian measure, and point it out real fast. So for example, like problem 1, 135 degrees, you can say, hey, that is 3 pi over 4 radians, because that's what is right up here with 135 degrees. The way we did it yesterday, we did these exact problems. We did 135 times pi over 180, which you could still do. And you get 135 pi over 180, and then you just have to simplify, and this ultimately simplifies to 3 pi over 4. So having the table is going to help us save some time on some of these problems. Unfortunately, it's not going to work for everything, because like the second one, negative 50 degrees, I'd have to go negative, and negative 45 degrees gets me to this 315, but it doesn't give me a negative 50, so I'm going to have to do negative 50 times pi over 180 and actually solve this one like we did yesterday. And I get negative 50 pi over 180, divide by 10, and I'm going to get negative 5 pi over 18. That'd be problem 2. Problem 3, 5 pi over 4. I'm going to check my table. There it is. 5 pi over 4 is the same as 225 degrees. Save myself a little bit of time there. Problem number 4, pi over 10. Unfortunately, we don't have one of those. So we have to use the conversion method we talked about yesterday, and we're going to multiply by 180 over pi. And I get 180 over 10, because the pi's go away, and 180 divided by 10 is 18. So pi over 10 is the same as 18 degrees. All right. And that's the idea for this problem here. Okay. Any questions on this circle or these 4 problems? Anything like that? So far, we're so good, hopefully. I think the key for these problems, you just have to really think about fractions. Think about it as fractions. Radians go up to 2 pi for a full circle. So you're looking for the number 2, and then you can split it into like 1/4, 2/4, 3/4, 4/4. That's half the circle. 5/4, 6/4, 7/4, 8/4. That's the whole circle, and that's broken into 45 degrees, or pi over 4 radians. All right. So that covers that first part today. Any questions before we move on? Okay, great. So what we're talking about today then is we're going to get a little new vocabulary. We're going to talk about arc length and area of a sector. So a sector, first we'll start with that, is a region of a circle bounded by 2 radii. And an arc of a circle. All right, that's what a sector is. So over here we can see 1 radius. Here's another radius. Those are the 2 radii. And then the arc is called the arc, the length of that arc. And then the sector would be everything inside that region. So it'd be this shaded area here. That's what a sector is. The other thing we have is a central angle. A central angle is the angle formed by the 2 radii. So this would be our central angle here. So 2 radii, it's the angle is formed between those 2. It's represented by this symbol, which is the Greek letter theta. It's pronounced theta, T-H-E-T-A. And it's like a circle with a line through it. There's a better drawing of it down here that I just highlighted. That's what central angle looks like. Angle theta. Okay. So now to find arc length and area of a sector, there are two ways we can do things. One is there are two formulas that I can give you, and I will give you those two formulas. But the formulas don't really explain the context of it. If you remember like how to find, like for example, the area of a whole circle, then you can think about it, circles as fractions instead. If you're just taking a piece of the circle, maybe that will help you. Or if you know how to find the circumference of a circle, which is like the perimeter of the circle, you should be able to find an arc length again by using fractions. And personally, I think that's a little easier than learning these two new formulas today. But I'm going to start by giving you these formulas. First formula, arc length is represented by the letter S. And it is r times theta. That's arc length. Basically, the radius times the central angle will give you the arc length. Area is represented by the variable a. It's 1/2 r squared times theta. Okay? There's one catch to using these formulas. Very, very important. And when you use these formulas, theta must be in radians. To use these formulas. If theta is not in radians, you have to convert it. It even says it up here. Central angle theta measured in radians, not degrees. All right, otherwise these formulas will not work. Okay, so basically, if you know the angle measure in radians, then you can calculate the area, you can calculate the arc length, as long as you know the radius and the angle measure in radians. All right, but what I would recommend, thinking about these instead, think about like an actual circle. Oops. If I did area of a circle, anyone remember the formula for area of a circle? A equals pi r squared, or circumference of a circle circumference was either pi times d, but I'm going to use 2 pi r instead. 2 pi times the radius. Well, guess what 2 pi represents? Radians. Circumference of a circle is the entire radians, 2 pi times the radius. So what you could do with a circumference problem is, like, let's say I want to find this arc length here. This is a 90-degree angle. How much of the circle is that arc length? That is 1/4 of the circle. So I could do arc length. I know that's 90 degrees. I can say 2 pi times, we'll say there's a radius of 3, times 3 times 1/4. I don't even need the angle in this case. I'm just going to find the circle and the circumference of the whole circle, and I'm going to multiply it by 1/4. Because if I know the perimeter of the whole circle, I can find the perimeter of 1/4 of it as well. And that's how I could find the arc length a little differently. I don't even need that 90-degree angle, which is nice. Because that means if I don't have an angle, I know how to solve this. There's 4.71 would be my length about. Same if I were doing area of the circle. Area equals pi r squared. If I multiply that by 1/4, that'd be the area of 1/4 of the circle. So again, I don't need any angles. I just say What's R? R is 3. And I'd find my area that way. These are just numbers I made up. That's where they're coming from. Okay. So pi times 3 squared divided by 4, or times 1/4. And I end up getting 7.07 for my area. Okay, that's how I could do this with these formulas instead. If I already have these formulas memorized and I don't want to memorize new formulas, I don't want to mess with new formulas, these formulas are great way to do things. All right, just an idea there. Let's do one example together. So a softball field forms a sector with dimensions shown. Find the length of the outfield fence. So that's the first thing, the length of the fence. So that's an arc length problem. And then find the area of the field. So area would do this whole thing. That's what we want to do. Well, first, if I'm doing the arc length, the temptation is to say, oh, Mr. Street just taught us this new formula. We do 180 times 90. And remember, this is in feet. So if I just did that and wasn't really paying attention, and I got 16,200 feet as my answer, I mean, think about a mile. 1 mile is 5,280 feet. So this is saying the fence is over 3 miles long. So that doesn't make too much sense to me. So don't use degrees. If I want to use this formula, I have to convert that to radians, but thankfully I have that written down up above as pi over 2. I could just multiply this by pi over 2. And I end up getting something like 282.74 feet. That would be the length of the outfield fence. That makes a whole lot more sense than 16,000 feet, which is, like I said, over 3 miles long. So putting the problem into the context is important. If I did the other form I was just talking about, we'll do this in red, or I do circumference, 2 pi r times, in this case, 1/4, because it's 90 degrees, that's 1/4 of the entire circle. I could do that as well. And I would say 2 pi times 180 times 1/4. And put that in my calculator, I would get the exact same answer. So it's entirely up to you. Whichever method you guys prefer is the one I would recommend you using. But I like this one because I already know circumference and I don't have to worry about the angle too much. That's why I like this method. Okay. For the second problem, area, since I already have the angle here, I'm just going to use this area formula up above. 1/2 times 180 squared times pi over 2. I end up getting the total area of the field. It comes out to 25,447 feet squared when it's rounded. Or I could do area of the whole thing, pi r squared times 1/4. Just pi times 180 squared times 1/4. And I end up getting the exact same number, 25,447 feet squared. Either method works for you. One of them is using the radian measure, one of them is not. That's the only difference with those two methods. All right. I got 2 problems here. I want you guys to go ahead and figure out these 2 problems. Spend a couple minutes working on these. They're kind of tricky. The first one is about the Space Needle in Seattle. Circular restaurant on the Space Needle. has a radius of 47.25 feet. So it says it completes one revolution in about an hour. So best way I can say this is 60 minutes is one full circle. That might be able to help you out there. 60 minutes is one full circle. And we're in the restaurant for almost 2 hours. So think about how many feet do you revolve total? So what's your total arc length if you've made more than one full revolution? Almost 2 revolutions. All right. And then for part B, you're going to find the area of each pizza slice. And then you want to compare the prices to their area and figure out which one's the better deal. I'm going to give you guys a couple minutes to work on that right now. Let me know if you have any questions at all. Let's go ahead and look at the first problem here. It says, how many feet do you revolve? The best way to think about this one is, the way I thought about it at first was that you're going almost 2 hours around. So figure out how much do I revolve in the first hour? So we'll do the circumference equation, 2 pi r, and 2 pi times the radius is 47.25. It doesn't matter how much of the circle I'm using, I'm going through, this is going to be one full circle. And one full circle comes out to about 297 feet. And then the second time, I do 2 pi r, 2 pi times 47.25, but this time I need to do the fraction of the whole revolution. So this, I've been spinning for another 55 minutes out of 60 for a full revolution, so I'd say 55/60ths. That's what I would use to represent the part of the revolution that I completed. And that would give me another 272 feet. And then I can do 297 plus 272, and that would give me 569 feet. That's one way to approach this type of problem. I could also do this one with that sector area problem. It's going to be r times theta, where I know the radius is 47.25, but I would need to figure out what my theta is. And that's where this one gets a little tricky, trying to figure out what that theta is, because I would have to do 55/60ths times 2 pi. And that's how I would kind of figure out what my theta would be for this particular problem, which is kind of hard to see, right? Because I'm going to do the whole 55/60ths times 2 pi. And technically, I guess I would have to go, it wouldn't be 55/60ths either. It would be 115, because I'm going for 115 minutes out of 60. So I think it would be a little tougher to do it this way with this formula that I just gave you. I think it's more about just breaking it into recognizable parts and saying, I know how to find the circumference of a circle, and then I know how to find the circumference of a fraction of the circle. That's the way I would approach trying to solve this problem. The second part says, do diners seated 5 feet away from the windows revolve the same distance? So if they're sitting 5 feet in, their radius is going to end up like right here. It's going to be 42.25 instead of 47.25. And the simplest way to do that is to just look at circumference, 2 pi times 42.25, 2 pi r, and see what we come up with just for one revolution. And I end up getting 265 feet. So the answer is no, they do not revolve as far, which makes sense. There's a smaller radius. Smaller radius, and that's going to directly relate to how far they're traveling around the arc. Okay. Problem 2, a pizza shop offers two choices for individual pizza, as shown. All right, so here's the first one. Highlight that in blue. A 6-inch pizza, or 6-inch radius, The second one's going to be a 7-inch radius, but a 45-degree angled slice instead. Now, find the area of each slice. So first one, we'll do area equals 1/2 r squared theta. We can use that formula if we want. We just have to convert theta, look into our paper at the top and see 60 degrees, that's pi over 3. 45 degrees, that's pi over 4. And I'm just getting those from what we did at the very beginning of class when we filled out that form. So 1/2 times 6 squared times pi over 3 radians. That'll give me the area of the first slice, which I end up getting 18.84 inches squared. The area of the second slice, 1/2 r squared theta, is 1/2 times 7 squared times pi over 4, and that's going to give me 19.24 inches squared. So the second one clearly has a bigger area than the first one. All right, it's about a little less than an inch bigger, so not a huge difference, but it's definitely bigger. Now the second part says, which slice is the better deal? So, I mean, looking at it, I see the 6-inch slice is $1.50, the 7-inch slice is $1.70. So it's kind of hard to tell because the 7-inch slice is bigger, but it also costs a little bit more, 20 cents more to be precise. So what we'd want to do then is we want to calculate like our expected value and figure out how much better of a deal is one than the other. So for the first one, it was $1.50, so I'm going to do 1.5 divided by the area, and I'm going to find the price per square inch. Okay. And this comes out to 0.0795 whatever dollars per square inch. So it's essentially about 8 cents per square inch, right? If we rounded that up, because $0.07 is the same as 7 cents, but because it's 7.9, we'd round it up to 8. So it's about 8 cents per square inch. The other one, I would do $1.70. Whoops. Divided by that area, 19.24. And that comes out to 0.08834 dollars per square inch. So the second one essentially is almost a full penny more. It's about 9 cents per square inch when you round it up. So even though the first slice is smaller area, it's actually a better deal. So the 6-inch slice is a better deal. Not by much. I mean, it's about a penny difference, so they're fairly competitive. But if you wanted to make them more competitive, how could you change the price of the 7-inch slice? And what I would recommend is like a guess and check here. Let's try dropping the slice price by 5 cents and seeing what happens. So we just do 165 divided by the 9.24. 19.24. And we get 0.085. So it's still a little bit more. We try 160 divided by 19.24. And that's going to come out to 0.083. 155 divided by 19.24. So I'm literally just guessing and checking at this point. And this one comes out to 0.0805. That's very, very close to the other one. So How would I change the price? I would say drop the price about 15 cents. And now they're going to be much more evenly priced. All right, so about 15 cents cheaper for that second slice, and they'll be about the same cost for each one. So you won't have the 6-inch slices selling out once people get the word out that that's a better deal. All right, so that's the idea for these last two problems. Tomorrow, you guys will have a graded assignment